Well, thank you, Professor Anton Baranov from Saint Petersburg University, to agreeing to deliver a talk at our seminar. Thank you, and please go ahead.
Thank you very much. And first of all, of course, I want to thank the organizers for inviting me to speak at this very interesting, very important seminar, which exists already quite for some time. And it's a special honor that I speak at this very special period when the seminar celebrates its 5th anniversary. Thank you very much. So my talk will consist essentially of 2 parts. And the first part, I will speak about existence and description of these bases of reproducing kernels in Fock-type spaces of entire functions. So this is a very classical group of questions in the spaces of analytic functions. And in the second part, I'll speak about applications to time frequency analysis, description of Gabor frames generated by some window functions, special type. Rather unexpected, it turned out that these, well, at first glance, rather different topics, they turned out to be very closely related, and some results from classical complex analysis turned out to be useful, have some unexpected applications in the time frequency analysis. So let me start with the very general setting, a description of problems in the general setting. So let H be reproducing kernel Hilbert space whose elements are functions analytic in some domain omega. What it means that it's a reproducing kernel Hilbert space. This means that for any point W in the domain, the evaluation functional at the point omega is continuous. Therefore, it is generated as an inner product with some function, which we denote Kw, which is called reproducing kernel at the point W. So inner product with this function gives us the value at the point W. Let me very briefly recall some very classical examples. One of the probably most important space of analytic functions is the Hardy space in the unit disk. H2, its reproducing kernel is the classical Cauchy kernel. Another well-known example is the Bergman space, H2 in the disk, and its reproducing kernel called Bergman kernel is essentially the square of the Cauchy kernel. Another example is the Perry-Wiener space. What is a Perry-Wiener space? It consists of all entire functions of exponential type at most A, whose restriction to the real axis is square summable. Or equivalently, by the Perry-Wiener theorem, this is the Fourier image of all space of functions, which are in L2 on the interval from -A to A. And in this space, it's also reproducing kernel Hilbert space, and the reproducing kernels are given by this formula. They are known as cardinal sign functions or sinc functions. And so this is also a very well-known example. And finally, the Bargmann-Siegel-Fock space, this space which consists of all entire functions, which are square summable over the whole complex plane with the Gaussian weight, radial Gaussian weight. I will define these spaces Fi formally. And so let me introduce 2 notions which will be very important for the remaining of the talk. These are notions of sampling and interpolating in the space of analytic functions. So assume that we are given a reproducing kernel Hilbert space H, and we are given a sequence lambda n in the domain omega, where all our functions are defined. Then we say that this sequence is a sampling sequence for H if there exist positive constants A and B, such that for any function f, we have this estimate. So what we have in this sum in the middle, we take values of our function at the points lambda n, so to say samples, and then we take their weighted L2 norm, where the weights given here are inverses to the norms of the reproducing kernels, to the power -2. This choice of weights, it is very natural, it is unavoidable. You cannot have anything meaningful if you consider similar estimates with other weights. The weights are very natural here. And so we want to have this sort of an estimate. So in other words, we can approximately compute the norm of the function f using the samples, using the values of our function on this sequence. That's the idea of sampling. So we are working in the reproduced kernel Hilbert spaces. Those are spaces whose elements are functions analytic in some domain omega, and for which the evaluation functionals for any point omega w in omega are continuous. And so these evaluation functionals, they are of course generated by in a product with some fixed function, which we denote by kw, and we call it reproducing kernel at the corresponding point. So f of w can be obtained as this in the product. So maybe I will skip these examples for the moment, but I will return to them a bit later. And so let us move to the second slide. Tatiana.
Yes, I'm trying.
Okay, maybe not the second part of this slide, if possible.
The slide before.
We shouldn't open the lowest part. But anyway, doesn't matter. Okay, so the two most important notions for this talk will be sampling and interpolating sequences for a given space. So if we are given a space, we are given a sequence lambda n of points in our set omega, we say that it's a sampling sequence for the space H if there exist two constants a and b, such that for any function f in our space, we have the following estimate, where in the middle we have some weighted L2 norm of the samples f of lambda n values of our function on this sequence. And we want this sum to be estimated from below, from above, by the norm of f squared with some constants a and b, which of course do not depend on the function f. So the idea of sampling is that it allows us to compute approximately, of course, up to some constants, the norm of the function f from the samples, from the values of the function at these points lambda n. And a second notion is notion of interpolating sequence. The sequence is said to be interpolating for H if we can interpolate any data from some weighted L2 space, again, at these points lambda n. So for any sequence Cn in L2, we can find a function f in H such that the f of lambda n is equal to Cn up to some weight. And now if you comment about these weights, you see here we divide by the norm of k lambda n squared. Here k lambda n, again, the norm of the reproducing kernel appear as the weight. And this choice of weights, it is unavoidable. It is natural, and you cannot have anything meaningful here if you consider other choice of weights in this sum of here. So this is how it should be. And finally, if such a function f, which solves this interpolation problem, is unique, then we say that the sequence lambda n is a complete interpolating sequence. And equivalent definition is that complete interpolating sequence, one can show that it's equivalent to the following property. It is both interpolating sequence and a sampling sequence. And now I would like to return to the previous slide and to the examples. So given a space of analytic functions, it's a very natural question, which is the basic question, which is always studied. How can we describe sampling sequences, complete interpolating sequences, interpolating sequences? Because it's very natural. If you're given a space, of course, you want to understand how the elements, how the functions of this space behave on a given set of points. For example, on which points, if you know the function on this set, you know the whole function, which sets define our function uniquely. Sampling is a stronger notion. It's not only uniqueness, but also we want to have this approximate formula for the norm, etc. But the problem is that many classical spaces, they do not have sampling sequences or complete interpolating sequences. And now let us look at some classical examples. So one of the most known spaces is the hardest space H2 in the disk. Its reproducing kernels are just classical Cauchy kernels. And in this space, there exist no sampling sequences, because as soon as we have this upper bound in the sampling inequality, then we already have unique non-uniqueness set. We already have a function which can be 0 on this set. We don't have then the lower estimate. Bergman space, A2 function square summable over the disk analytic functions. The kernel here is the Bergman kernel It's given by this formula, square of the Cauchy kernel. And in this case, there already exist sampling sequences, and they are there is a well-known description of them by Christian Sape, but there are no complete interpolating sequences. So sampling and interpolation, in this case, they become incompatible. And in the Perry-Wiener space, this is a space of all entire functions of exponential type at most a, this parameter a, whose restriction onto the real axis is square summable. And this space, by the Perry-Wiener space, it consists of Fourier images of all functions f in L2 on the interval from -a to a. And in this space, the representative kernels are given by this formula. These are so-called cardinal sign functions or sinc functions. And in this space, there exist complete interpolating sequences. There exist, and they are given by, for example, we can consider sequence points, which is just integer lattice, well, divided by this coefficient a, and corresponding system of reproducing kernels will be on orthogonal basis, and then we have both interpolation and sampling, everything. So we have complete interpolating sequences in this space. And the Bargmann-Siegel-Fox space, this is a space of all entire functions, which are square summable over the whole complex plane with the Gaussian weight. In a second, I will define the general spaces f phi. In this case, the producing kernels, they have a very simple form. These are just these complex exponentials. And the situation is again as in the Bergman space. There exist sampling sequences, and there exists description of them. I will present it very soon, but there exists no complete interpolating sequences. Okay, so these are a few examples. Let us now go to the next slide, please. So let me now mention the following. So we introduce these properties of sequences, interpolation, sampling, and these properties can be rephrased, closely related to the geometric properties of the corresponding systems of reproducing kernels. For example, lambda n is a sampling sequence. This means, literally means, that the system of normalized reproducing kernels corresponding to these points is a frame for the space H. Here in the brackets, I recall the general notion of the frame. A sequence Fn is a frame in this space H. If we have this approximate Parseval identity, we can again compute the norm up to the constants, looking at the in L2 norm of the inner products. And you see immediately that what is written here is exactly the definition of frame applied to this system of normalized reproducing kernels. And for example, lambda n is an interpolating sequence for the space H. This is equivalent to the following property, that the sequence of normalized kernels is a Riesz sequence, namely that is a Riesz basis in its closed linear span. And finally, if lambda n is a complete interpolating sequence, this is equivalent to the property that the system of normalized reproducing kernels at the points lambda n is a Riesz basis in the whole space H. So when we study these notions, actually we study geometric properties of the corresponding systems of reproducing kernels. Okay, please, let's go to the next slide. So now I will introduce the Fock type spaces. So let phi be a function defined on the ray, which goes to infinity sufficiently fast, at least faster than the logarithm. And then by f phi, I will denote the following class of functions, entire functions f, for which this integral is finite, integral over the whole complex plane with the usual planar Lebesgue measure, modulus f of z squared with the weight exponent of -2 phi of modulus z. So it's a radial weight. And then it's easy to see that this is a reproducing kernel Hilbert space. Moreover, since the weight is radial, you can see that actually monomials form here an orthogonal basis. But it's not so important for us, and for we are interested in reproducing kernels. And for the classical Bargmann-Siegel-Fock space, a very popular space which plays an important role in many questions, in quantum mechanics and time frequency analysis, so in many various applications. And so this is given by the case when phi of r is a quadratic function. So the weight is a Gaussian, symmetric radial Gaussian weight. And reproducing kernels in this case, these are just these exponential functions. And so the concrete question that I want to discuss now is the following. Do there exist complete interpolating sequences for the space f phi? Or, in other words, do there exist Riesz bases of normalized reproducing kernels in this space? And if it happens that the answer to the first question is yes, then, of course, the next natural question is how to describe all such bases, all such Riesz bases, all complete interpolating sequences. Well, but in fact, unfortunately, in most of the cases, the answer to the first question is already no. There exist no complete interpolating sequences for these spaces, and now I will explain why this is the case. So please let us move to the next slide. So sampling and interpolating sequences for the classical Bargmann-Fock space with this Gaussian weight, they were described by Sape and Wollston and independently by Lubarsky in the beginning of the 90s. And let me present the description of sampling sets, of sampling sequences, which is actually very simple, very geometric. The proof is not simple, but the description itself is quite simple and geometric. So let's see. So assume that we have a sequence lambda separated just in usual Euclidean distance, and then it is a sampling for the classical space with this Gaussian weight with pi r squared. Of course, this normalization here is important. The results should be slightly different depending on the constant here. So for the constant pi, if and only if the following lower density is greater than 1, the lower density of the sequence lambda. How this density is computed? Very easily. First of all, we fix some r, some radius, and we look at the intersection of the set lambda with balls of radius r at some point z, and count the number of points in this intersection. And then we move this ball of fixed radius over the whole complex plane. For any z, we compute this number of points, and we take the infimum, the smallest number of these points. And then we divide this by the area of the corresponding disk, by pi r squared. And finally, we take the lower limit as r tends to infinity. So we take, first of all, the worst ball for any given r, divide by its area, and normalize, and then take r tend to infinity. And this lower density must be strictly greater than 1. This is an if and only if condition for being sampling in the classical Bargmann-Fock space. And I do not formulate here, but for the interpolating sequences, there exists a completely similar description. But in this case, what should replace the lower burden density by the upper density, d plus, where we take here not infimum, but supremum, the largest quantity of points. And we take here the limit, the upper limit, the lower limit. And this upper density must be strictly less than 1. And from this, of course, we immediately see that there exist no complete interpolating sequences. These two properties are incompatible because in one case, the lower density must be large. In the other case, the upper density must be small, strictly smaller by the same number. So they never meet these conditions. And this phenomenon, it actually happens in many other examples of the Fock-type spaces. There was a series of work. I mentioned here a couple of them. For example, Marca Massanega and Ortega-Cerda, they proved this in the case when phi is a subharmonic, of course, when continued radially symmetric to the complex plane, and its Laplacian is a doubling measure. Whatever it means. And Boric and Kille, they proved this for a much wider class of weights, growing very, very fast, like exponentially, which are not doubling. But always the results are the same. There exists some appropriate density, which should be, of course, it depends on the weight in some sense, but it's always some density which is responsible for being sampling, for being interpolating. Always there are some strict conditions of this type, and these conditions never meet. So in all of these cases, there exists no complete interpolating sequences in this space. Let us go further, please. And the first example of a situation where in a Fock-type space there exist complete interpolating sequences was obtained by Borichev and Lubatsky in 2010. Moreover, they found a sharp bound for this phenomenon. So the result is as follows. Assume that phi of r is of this form. Some coefficient which is not positive, which is not important, of course, log to the power beta of r, where beta is between 1 strictly and 2. If beta is 1 or smaller, then it's simply a space of polynomials or just empty zeros set, so it's not interesting. So for any weights of this type, in this space, there exist complete interpolating sequences. And in a sense, this weight log squared, it turned out to be exactly this sharp bound for this phenomenon. Because if we introduce the following quantity, which is very often used, very useful in the study of this Fock-type spaces, we take the Laplacian of phi to the power minus 1/2, which is, in our case, when phi is a monotonic function, is simply given by this, this formula explicitly. So if this rho, for example, for phi of r equal to r squared Gaussian weight, it's a constant. For the weight log squared, this rho, it grows like r. And so the theorem is like this. If this rho of r is O small of r, and this means that this weight grows faster than this logarithm squared. So if the rho of r is O small of r plus some additional regularity, then there are no complete interpolating sequences in the corresponding space. So indeed, this log r squared, this is, in a sense, a very sharp bound for this phenomenon. For weights which grows slowly, we have complete interpolating sequences. For weights which grow faster, we do not have them. So that was a very nice observation, very nice result. Let us move a bit further. Since then, it was generalized by several authors, by myself, Yuri Belov and Alexander Borichev, and then there were very nice results by Isaev and Yulmuhametov, which came very, very close to give an if and only if conditions. Again, you see in the Borichev-Lubatsky work, there were also only some concrete examples like this logarithmic weights, and then this also can be formalized and to have some, to show that for some class of weights of slow growth, we always have such complete interpolating sequences. I will not go into detail here. But now let us consider in more detail the case when phi of r is equal to this log r squared. Let me introduce here this normalization factor 1/2, which is of course not so important. And let f be the corresponding Fock-type space with this logarithmic weight. And jointly with a colleague from Bordeaux, Dumont, Hartmann, and Kelly, we found a full description of complete interpolating sequences for this space. Because in the Borichev-Lubatsky, they simply discussed existence, whether they exist or not, and they gave the answer. And all these results also, they are about existence or non-existence, but there is nothing known about description of such complete interpolating sequences. And already 10 years ago, we managed to find such a full description of complete interpolating sequences for this specific space. And this description turned out to be very beautiful, very geometric, very simple to state. And now I want to state this description of complete interpolating sequences for this space. So Tatiana, please go to the next slide. So here I simply repeat the definition of our space. And so what was the description? Borichev and Lubarsky, they show that there exist complete interpolating sequences. Moreover, they produced an explicit example. This sequence of exponentials e to the power m in the space with this normalization is a complete interpolating sequence for f. This actually, by the way, I should have said that, of course, this space of entire functions, which are summable with this weight, these are functions which grow very, very slowly. They are in transcendental entire function, of course, but they grow, they all functions of zero order, for example. They actually grow very, very slowly because this weight, of course, in a sense, it's an upper estimate for the growth of the function. So of the function, they grow like log squared divided by 2 at most. So Lubarsky and Borichev, they show that such a system is a complete interpolating sequence, and it turned out that it is possible to give a description of complete interpolating sequences in terms of deviations from this fixed, already known complete interpolating sequence. So the result is of perturbative nature, but it's unexpectedly, it gives not only usually perturbative results, usually they give some sufficient condition. You have some class of good sequences, you perturb it a bit, and then your property preserves. But usually you cannot describe all class of your objects using only perturbations. But in this case, we can, which is also a bit unusual. So the result is like this. Assume that lambda n is a lambda n. We have a sequence, and we write it in this way: exponent of n, exponent of delta n with real delta n. So it's a perturbation, it's deviation of the modulus of the lambda n from e to the power n, and finally some argument theta n. It's going to be e to the n. And so such a sequence lambda n written like this is a complete interpolating sequence for our Fock type space, if and only if we have the following three conditions. First of all, we should have, of course, some separation condition, because separation always is a non-separation. Yes, we have closed functions, we cannot interpolate. Of course, it's always an obstacle. So separation is this separation in this hyperbolic metric, in a sense. So lambda m minus lambda n is estimated by the norm of lambda n with some constant gamma positive. The second condition is that the sequence delta n is bounded. But that's not enough. The third condition is that this perturbations delta k, that should be smaller than some constant, but not individually smaller. They should be smaller in the mean. Namely, there exists some sufficiently large number n, large, such that if we consider sums of these perturbations delta k over all intervals of lengths, n large, take the modulus divided by take the mean divided by n, and take supremum over all n small. So this n small is the moment where we start. And this supremum should be strictly less than 1/2. So individual perturbations, they can be sufficiently large. They need not be smaller than 1/2, but they can be of different sign. Of course, there should be some compensation of the means. So that's very geometric, very explicit. Note also that these conditions of this theorem, they essentially do not depend on the radius, on the argument. They depend on the radius, essentially delta n, but on the argument, they almost do not depend. Of course, they depend a bit, because in this separation condition, when you choose the argument, at some moment you can lose it. But that's the only place where this is important. In all other places, they are of no importance, these arguments. Okay. So this was the description that we obtained for this rather special class of space of entire functions. Well, its interest, of course, was related to the fact that it was this limiting example in the results of Borichev and Lyubavsky. This was exactly this limit space where we still have this phenomenon where we have these bases of normalized reproducing kernels. But otherwise, it was not clear why it's really so interesting. But once we have such a beautiful description, of course, that was already nice to have it. But still, it was like some toy example. And more recently, it turned out that this space, it appears naturally in some questions related to time frequency analysis. And moreover, this description that we have here, it turned out to be useful to study the so-called shift-invariant subspaces, which appear in time frequency analysis. And this is the second part of my talk, to which I will move. So maybe just one more, very shortly, I mentioned one more result in relation to this condition. This condition, it resembles a rather well-known condition from the theory of exponential bases, which is the so-called Avdonin condition. So let us move to the next slide. So very briefly, I have to mention, there is this condition of this type, it appears, but in a very different setting. So it's not really related to this, but the condition is essentially the same. So it's a very classical old problem posed by Perry and Wiener in the 20s, beginning of 30s, how to describe exponential Riesz bases in the space L2 on the interval, say from -pi to pi, where lambda n are some real numbers or complex numbers, but not our standard orthogonal bases, of course. Yes, and in other words, it's equivalent to the description of Riesz bases of cardinal sign functions or complete interpolating sequences in the Perry-Wiener space, because if you take the Fourier transform, such sequences, they are mapped to sinc functions unitarily, and so it's the same problem. And one of the very beautiful results in this direction was the so-called Kadit's 1/4 theorem, which says that if you take a small perturbation of our classical orthogonal orthonormal basis, exponent of I and t, where n runs through all integers, and now assume that lambda n, they differ from n by at most 1/4. Namely that the supremum is less than 1/4. Then the corresponding system is a Riesz basis in the space L2 from -pi to pi. And 1/4, it's an exact sharp value. You cannot make better. And Avdonin later showed that, in fact, this condition, this sufficient condition, can be relaxed, and we need not have all perturbations be smaller than 1/2 individually. It is enough that they are smaller than 1/2 in the mean. And the condition, the quantity is exactly the same. We consider this right lambda n as n plus delta n. I assume that, for example, they are all real. Delta n is bounded. And then it's if in the mean they are smaller than 1/2, then it's a Riesz basis. But in contrast to our theorem, of course, this is only a sufficient condition. And for the problem of Perry and Wiener, you simply cannot give an answer in the perturbative form. You cannot describe everything as small perturbations of integers. A complete description was obtained later by Pavlov and then extended by Pavlov, Nikolsky, and Khrushchev, and the descriptions in terms of Mackenhaupt or Helsinki condition. That's much more deep and complicated than that, but still, this condition really looks very similar to what we got in the Fock type space. So let us go further. Please, let's. Okay, so now a few words about the time frequency analysis and Gabor systems. So one of the classical tools of the analysis of signal is a short-time Fourier transform, which is given by this formula. The idea is that instead of taking the usual Fourier transform, we also introduce some window function g with some good localization, and we take here consider here such shifts and then take the Fourier transform. And then we get not a function of one variable, but we get a function of two variables, which gives us much more information about the signal, because it gives us not only its localization in frequency, but also its localization in time. And again, if you want to study such representations, very important is to be able to discretize them, because we cannot work with continuum of data. We need to take some discretization. And therefore, one considers not all values of x and y, but only some discrete but sufficiently dense lattice, for example, of values x and y. And then one introduces the so-called Gabar systems, which are systems of the following form. So this function I will denote like this, mytx, so translation in x, modulation in y, multiplication by this exponential. And the Gabar system, it consists of all such time frequency shifts, they're called time frequency shifts, these functions, when x and y runs through some lattice. Then m's are subsets of real numbers, usually discrete sets, countable sets, and then we consider such lattice. And the standard situation, of course, one considers just integer lattice with some coefficients, positive coefficients, alpha and beta, but not necessarily. Sometimes people work also with more general lattices, but the most standard case is like this. And so the natural question, please let us move further. The natural question is is the following: if we have such a sequence of time frequency shifts, for which, for example, parameters alpha and beta, such a system will be a frame in the space L2 of R. And this goes back to Gabar, who introduced it again in relation to some physics problem. I will not go into detail here, of course. So the typical situation is when we can have the lattice alpha z times beta z, where the product of alpha beta is strictly less than 1, or less or equal to 1. As soon as it is greater than 1, it simply never is a frame, so this condition is natural. And there exists some heuristic principle that if our function g, our window function, is sufficiently good, for example, smooth and also decays fast, then the corresponding Gabar system is a frame if and only if this product alpha beta is strictly less than 1. We need not need of them, both of them be small. It's enough that one is small, then we can have a better, more dense set of value of data on one direction and more sparse in the other. So what the important is the balance, that is the product. Alpha beta is less than 1. It's a necessary condition for such good functions, and the question is whether it is necessary, whether it is sufficient or not. And there exist many results for many different classes of window functions. On the other hand, there is no general theory. Always for each function there is some specific methods which work in this case. Most of these results are quite complicated, but there is no general method given a function g how to show that such a sequence is a frame. So please let us go to the next slide. Here it's a brief list of some known results known up to now. The classical case of the Gaussian function, one of the most popular window function, this exponential function, symmetric exponential function, asymmetric exponential function, hyperbolic second. Then more recently, Gröchenig and Stockler, they obtained some results for some classes, but rather narrow classes of functions, which are defined here, but I will not go into this. So quite recently, there is a very interesting work by Belov, Kulikov, and Lubarsky, who solved this problem for such rational functions of this form, finite sums. So, but this was just a some list of known results. Let us go further, please. Well, but this was what was written on the previous slide. It was only for this lattice, frames, and almost nothing is known about description of regular frames, where lambda and m are just some discrete separated sets on the line, but not lattices. And also one even can consider a more general question, and to take some set S, again some separated set, for example, on the plane, and look at the time frequency shifts corresponding to points xy in this set S. But this problem is completely open. The solution is known only for the case of the Gaussian, and it's simply the same result of Sape, Wollston, and Lubarsky, which I already stated, because again there exists some unitary operator which transforms the question about Gabar systems corresponding to the Gaussian function to the Bargmann-Siegel-Fock space with the Gaussian weight, where this time frequency shifts, they are mapped to normalized reproducing kernels. So the question whether we have a frame, Gabar frame of time frequency shifts, it's the same to say that we have a frame of normalized reproducing kernels. That is, we have a sampling sequence. And for the sampling sequences, we know the answer. This is the same answer, the same theorem, which I already presented, where we have this lower burden density must be strictly greater than 1. Well, let's go further, please. So now let us consider what is called semi-regular frames, where one of the sets is usually lattice, alpha z, but the other set is some arbitrary set lambda, separated subset of the real line discrete set. And then in this case, Gröchenig, Romero, and Stockler, for some different classes of functions, they obtained a similar description. There are several results for different classes, in particular for hyperbolic second, which is more recent. And then the following statements are equivalent. The corresponding system or Gabar system is a frame in L2 of R corresponding to lambda times alpha z. The dual lattice alpha z times lambda also generates a Gabar frame in L2. And the main condition is, again, in terms of some density. And it's, again, a Berlin-Glower density, but not a planar density, as in the previous theorem by Sape and Wollston. A usual density on the line, but the idea is, again, the same. We consider the number of points of lambda in the interval from x to x plus r, and we shift this interval of fixed length r along the line. Take this intersection, can count the number of points, take the infimum, the worst case, divide by r, the length of the interval, and take the limit as r tend to infinity. Limit or upper limit, but there, this is the same. So everything, again, is expressed in terms of density, lower Berlin density of this set lambda. Well, please. Let's go further. And how one can obtain such results, how Gröchenig and his co-authors worked. One of the main tools here is the so-called shift-invariant space. So these are now the shift-invariant spaces from the title of my talk. So for G, function G in L2 of R, we consider the following space. We consider all shifts, integer shifts of our function G with square summable coefficients Cn. We consider all functions which can be represented in this way, and we consider it with a standard L2 norm. Of course, this makes sense if we assume additionally that our function G has the following property, that any function represented in this form its norm is L2 norm. It's comparable with L2 small norm of the coefficient Cn. So this requires some sufficiently good localization of a function G. So we assume that function G has this property. And then with such a function G, we associate such a space, such a subspace of L2 on the line. For example, the classical Perry-Wiener space, it also coincides with the shift-invariant space generated by this cardinal sign function sin pi x divided by x. And it's against the Shannon-Kotelnikov sampling formula. It exactly gives us the equality of these classes. And now we introduce the notion of sampling for the shift-invariant space. It's very similar to the case of spaces of analytic functions. The only difference that here we simply consider unweighted L2 norm of the samples. So we can say that sequence lambda is a sampling sequence for V2 of G if the norm of F can be estimated from below, from above, with some constant independent on F, of course, by L2 norms of this sequence of samples. And as I said, these shift-invariant spaces, they are a very useful tool when we want to study frames, Gabar frames of these forms, these semi-regular Gabar frames. The following theory was proved by Gröchenig, Romer, and Stockler, that the system, a semi-regular Gabar system, is a frame in L2 of R, if and only if the sequence lambda, and not only the sequence lambda itself, but also all its shifts, is a sampling sequence for the corresponding shift-invariant subspace generated by this window function. So the problem about Gabar frames is now reduced to the study of sampling in this shift-invariant space. So in a sense, two-parametric problem, it's now reduced to a, so to say, one-dimensional. Yes, only one parameter lambda now is present here. And it's a very useful reduction, which played the fundamental role in the results of Gröchenig and his courses. So let's now move to the next slide. So the following theory, Gröchenig, Romer, and Stockler, they described interpolating sequence, described sampling sequences for shift-invariant subspaces generated by this Gaussian window function, or more generally by some class of more general class of functions, which I mentioned in one of the previous slides. But let us think about the classical Gaussian case. So they showed that, again, one can give a description, or to be more precise, almost description of sampling sequences in terms of densities. But now it's no longer if and only if. It's only there is some gap between sufficient conditions and necessary condition. So each separated sequence lambda, for which this lower density is strictly greater than 1, is a sampling sequence for the space V2 generated by the Gaussian. But it's not even a if condition. But the necessary condition is much weaker. It said that if lambda is a sampling sequence, then lambda is a finite union of separated sequences. And it always contains a separated sequence, lambda wave. So this has the lower density, not strictly greater than 1, but greater or equal to 1. So here is the principal difference. Here it's strict inequality in a sufficient condition, but in the necessary condition it's only non-strict inequality. And this is unavoidable because there exist interpolating sequences, sampling sequences, which has exactly 1 this density, but which are still sampling sequences. So let's go a bit further. There exists, maybe also the whole slide, yes. There exists a similar notion of interpolation in shift-invariant spaces, here we just simply interpolate L2 data. We say that sequence is interpolating if for any square summable sequence there exists a function which f of lambda n is equal to an, and there exists a similar description of interpolating sequences, but again not a not a description. There is separately sufficient condition which says that upper density is strictly less than 1, and there exists a necessary condition which says that upper density is at most 1, but the quality is non-strict. So again, in terms of densities, we are not able to describe completely this interpolating sequences because there exists the critical case of critical density. All densities upper, lower, they coincide equal to 1, and in this case, we still can have a sampling and we can have interpolation. So let us go further. And now I present one of the main results of this talk using the methods of using the theory of these Fock spaces of slow growth, which I introduced in the first half of my talk. Jointly with Yuri Belov and Karl-Heinz Gröchenig, we were able to give a description, a full description of complete interpolating sequences for the space V2 of G, where G is this the classical Gaussian function, exponential minus ax squared. And what is a complete interpolating sequence? As before, it means that it's both sampling and interpolating. Or equivalently, this means that we always can solve the interpolation problem, and the solution is unique. And here is a description. So assume that we have a sequence of this separated sequence of points lambda on the real axis. Then we write this sequence lambda n as n plus delta n, as in this Kaditz or Avdonian type theorems that we discussed previously. We write lambda n as n plus delta n, so deviations from the integers. And in fact, more precisely, one should say like this. We have a sequence lambda. We can choose such an enumeration of this lambda, such enumeration, lambda n, enumerate like this, such that we have the following two properties. Delta n is bound, the sequence is bounded. And also this delta n, all are small. In the mean, they are sufficiently small. In the mean, they are less than some critical value. Namely, if you take again the sum of delta k, which can be both positive and negative, they can compensate each other. We take the sum of the lengths n large, starting from some n small. Take the mean, and then we take the supremum over all n in z. So again, we shift this interval along which we sign, we shift along the whole real line. And this mean must be strictly smaller than 1/2. And this is an if and only if condition for being both complete. It would be both interpolating sequence and sampling at the same time. And this is the first result in the literature where one could give a description of complete interpolating sequence for this class of shift-invariant spaces. It never was possible known before. And note also a funny thing that if we look at the integers and their shifts that shift the integer letters just by some delta, and then this sequence is complete interpolating sequence actually for all shifts delta except only one exceptional value when delta is equal to 1/2. That's funny thing that there is only one exceptional value where we lose the property of being a complete interpolating sequence. Okay, maybe let's go a bit further. Here, just very briefly, I want to say that, of course, this our result, which describes complete interpolating sequences, it also implies the previous results which I stated about description of simply sampling sequences or simply interpolating sequences in terms of densities. Because, for example, if we have a separated sequence with lower density greater than 1, then one can show, and it's not difficult to do, that then it contains a complete interpolating sequence using our description of complete interpolating sequences. And then it is sampling, of course. If it contains something which is a sampling sequence, then it is sampling itself. And if we have a separated sequence with upper density strictly less than 1, we can always append it to be a complete interpolating sequences. Of course, then the sequence was itself interpolating. So these cited results of Kravchenko and Stockler and Romera, they also follow from our result. Let's go to the next slide. Maybe just a few more words. We managed then to use this method to study a new class of window functions, which was not covered by the previous results by Kravchenko, Romera, and Stockler. These are which we call second type functions, hyperbolic second type, of course. So these are functions of this type, exponent of x, exponent minus bx, where a and b are even not necessarily real, can be complex numbers, but with positive real parts. We have a good decay at infinity, of course. And in this case, we have a similar description, which I probably don't want to go into details, but a very, very similar description that we can describe complete interpolating sequences for this space, shift-invariant space generated by this window function. Again, in terms of these deviations, very similar condition, only we should subtract some constant depending on this a and b to have the result. But but otherwise, it's very, 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 very similar to what we have. So we can get a description, again, a full description of complete interpolating sequences for this space V2 of G. And maybe the last slide. And here we stop. Because I said that these shift invariant spaces V2 of G, the spaces of shifts, they're of course also a natural interesting objects, but also they are interesting not only in itself, they're interested as a tool to study Gabor frames. They are an important tool to study Gabor frames. And as soon as we have results about interpolating, sampling, about complete interpolation sequences in these shift invariant spaces, we immediately can have some results about Gabor frames, semi-regular Gabor frames. So could we go to the next slide, please? So this is the last result which I wanted to show using our methods jointly with my colleague Yuri Belov from Saint Petersburg. We proved a result similar to the results of Kravchenko, Romera, and Stockler for classical hyperbolic second and for the Gaussian function, a description of semi-regular frames. The description of, again, is in this the same. The condition is the same. It's the density. It's a lower Berlin density, but the class of window function that we managed to apply this and to get such a criterion is a substantially new class. And all these results, which I mentioned in this part by myself and Belov and Karl-Heinz, they use the reduction of the problem using some transforms, some unitary transforms, to some spaces of entire functions, which essentially turn out to be this small Fock type space with this weight log squared, which we introduced. And therefore, we can prove for these results using the description of complete interpolating sequences for the Fock space. It leads to the corresponding results in the setting of time frequency analysis. And it's an interesting example when the complex analysis, it helps to solve some problems which initially do not have anything to do with complex analysis. And most of the results in this area, they are proved using some standard methods of Fourier analysis, some symmetrization techniques, Zach transforms. There is a lot of interesting machinery here, but usually it's not complex analysis. So it's interesting that we can use complex analysis to get some new non-trivial result in this area. Okay, so I stop here. Thank you very much for your attention.
Well, thank you very much, Professor Baranov, for a very nice presentation. And we have time for questions. So any questions, please welcome. Meanwhile, maybe I'll have just one general question. Are there any application of this theory to study of certain kind of classical operators in these spaces? Any kind of papers on this issue?
Well, operators. Well, maybe not completely directly this, but there are some results. You see these sort of spaces of slow growth. They appear naturally in the theory of spaces, which can be defined maybe in a slightly different way using the Cauchy type representations. But all these are, in a sense, equivalent. And there was an interesting result, which was proved even before our result with colleagues from Bordeaux about this description, of Riesz sequences, Riesz bases in such sort of spaces by Sape, Belov, and Mengster. And they were interested mainly in the boundness or other invertibility of the certain Hilbert type transforms. So this is indeed closely related to these questions. I can give you the reference to it. Very interesting.
Okay, please do that. Because if you have some kind of basis or representations, then you can have kind of a spectral representation for classical operators, maybe for kind of projections. Yes. And I understand that these small Fock spaces are very good ones. Can you give an idea what's the kind of behavior of functions, kind of power-like behavior when going to infinity they have, these functions from the small Fock spaces?
Oh, they are functions of very, very slow growth. So the weight, this weight exponent of -phi, it actually gives us more or less the exact order of growth which they can have. So they are functions of course, they're functions of zero type, of zero order, but it's much more stronger than that because these are functions which are measurized by exponent of log modulus z squared. Yes. So if you want to construct such a function, for example, looking at its zeros and constructing it as some infinite product, yes. How can you construct an entire function? Of course, you can write it in the terms of coefficients. But in terms of coefficients, all these Fock spaces, they're in a sense very simple because you immediately have its unitary equivalent to some weighted space. Yes, if you look at the Taylor coefficients, then of course you simply look at the norms of the powers in this z to the power n in this space, and these are coefficients. So in terms of coefficients, you can very easily, Taylor coefficients, you can very easily describe such functions, but then it's not very convenient to work with such representations, to work with such series usually. It's not so pleasant. Another way to look at a function is to construct it as an infinite product. And then, since you have, these complete interpolating sequences, you more or less know the zeros in this space because these complete interpolating sequences, they are also they are exact sets of zeros. If you take out just one point from them, for example, you already have a zero set of some function in this space. So you can construct the corresponding functions using, for example, these bases as such products, for example. So you can see how the zeros should go to infinity.
Okay. Well, thank you for your explanation. Well, maybe more questions?
May I ask quickly?
Yes, please.
Does the knowledge of explicit form of the reproducing kernel play a role in the proofs? I mean, for
No.
this. So
no, unfortunately, it's simply not possible, except for the example of the classical Bargmann-Siegel-Fock space, where we have these exponentials.
Yeah.
But for
So
all
for this
other,
one with the log square, you don't have a formula.
no. And more or
But
less,
would it be useful to
I
have a formula?
don't know any other example of a Fock-type space except this classical Gaussian case where we have an explicit form of the kernel.
Yeah,
usually
you can.
Possible.
No, you can build. It's not difficult if the form of the weight is like the Mellin transform is known. Then it's not hard to build a reproducing kernels. But
Yeah.
for this log square, I don't know.
No, for this log squared, that's definitely not possible.
And it would it be useful to know some formula, or it wouldn't help? So the knowledge of weight is more important than the knowledge of the kernel.
I would say that the knowledge of weight is more important. Well, perhaps it could be of certain help, but no, I don't think it's really so important in this.
Thanks.
Well, thank you. More questions, please. If there are more questions. Well, I don't see more questions, but we had already very nice discussion, and well, let us thank our speaker for very nice presentation.
Thank you.
Thank you, Professor Anton Baranov, for agreeing to deliver a talk at our seminar. As I said, it's a really pleasure for us because it has been 5 years since we started, and I just looked at the web page of our seminar, and we started on May 14th, so just exactly 5 years and 1 day. And let me take just maybe a couple of minutes of you. I just opened a web page of our seminar, and I'd like to show you our speakers. Anton Baranov will be also there on this page soon. Let me try to share my screen. Do you see my screen?
Yes.
Okay.
Yes.
Well, you can see this information on our web page, Mathematical Science Research Networks, fed.ru. Well, here our previous speakers. We have also partners, Tbilisi Analysis Seminar, Nikolsky Seminar, Yerevan, Vladikavkaz Center, and Seminar on Constructive Theory Functions from Saint Petersburg. And I'll just list our recent speakers. You can see countries from Russia, from Italy, from Uzbekistan, Chile, Georgia, Hungary, and so on. Again, Russia, Mexico. I'll just list all our speakers. It's really a great pleasure to have these researchers from all over the world, because some of them are our old friends, some of them are newcomers, but they became friends with us, so we keep in touch with our speakers. And as I said, it's a great pleasure to have such a great scientists from many countries. As I see, from Iran, from United States, from Emirates, so many countries. And well, I hope that this seminar will last for many years, and we will update our research community more and more. Thanks to everyone, thanks to every participant, thanks to every speaker who made this seminar. As I said, it's our great pleasure, and I'm coming to the very first our talk from 2020. And the seminar appeared in the COVID time, because before that we had a regular seminar, face-to-face seminar, but when COVID came, we just decided to make it temporary, but since then we understood that these temporary things should be permanent, and well, I hope it was a good decision. You see, 14th of May 2020 was our first seminar talk, and so we have 5 years of our work. Thanks to everyone. Let me see how to close this. Okay, I come back. Thanks again. Thanks to every participant, thanks to every speaker, thanks Professor Baranov, because participants and speakers are the people who create this seminar. They create this event. Thanks to everyone.